Hello, everybody. This is Professor Ma, and this is a summary on sequences. Uh, Two basic terms we are going to use are converging and divergence for the following few sections. Okay. The word convergence it means comes to has a limit. Converging means comes to a point. Converging. Okay. And the word divergence, diverging opinion. So it means we have these things scatter going on, or maybe it's going different route. And this we use in to describe the behavior of sequences. So a sequence in mathematics just order list of infinitely many usually numbers. Okay, that might have a pattern, and might not have a pattern. And so here are some sequence with patterns. R numbers, square numbers. Here's a sequence seemingly no patterns, but who knows? Maybe some aliens can say, "Oh, I know exactly what that is," and I suddenly don't. Okay, so whether it has a pattern or not actually is the basis of mathematics. We write the general notation for sequence. If you write a little bit more complete, we write as a set. And here is a formula based on function based on n, the integer n. And if we know what it is, we write it out explicitly. So if, for example, if one write a shorter, so we just simply write each term as a with an index n. So for example, here, the nth term is 3 times n plus 1, it would generate the sequence. So if I'm plugging n equal to 1, 2, 3, 4, and so on, we say it would generate the number 4, 7, 10, so on, so on. Okay. And we're going to omit writing infinity on top. Okay, the infinite many terms. Notice we can have many different formulas defining the same sequence. Here are two formulas that when you plug in the number 1, 2, 3, 4, you get 0, 0, 0, the sequence of zeros. We lot of many sequence we have flip-flop signs. For instance, if we take the derivative of sines and cosine, the plus and minus were flip-flops. So we will have sequence that with flip-flop sign. We call those alternating sequences. Okay, depending on the first one is positive or negative, depending on where the number n start, you have to choose one or the other. So for example, minus 1 to the nth comes these, and starting with n equal to 1. So the first number will be negative. And then it will be positive, negative, positive. It will alternate from there. And then you fill in the number. The numbers themselves are 1, 3, 5, 7, except with minus 1, the first one, plus, minus, plus, and so on in these patterns. And we can piece together formulas. Here's an example of piecing together formula. Notice it's a first we notice, oh, it's alternating. So this formula is going to come in somewhere. Then we notice these are other fractions. They have two parts, and the top part numerator are just even numbers, and then the other components down below are the denominator. They are the powers of 3. So we create formulas for the even numbers and powers of 3. And notice it starts with k equal to 0. Okay, so to match k equal to 0 to the number 2, for instance, the first, and then I have 2 times k plus 1. So I have to use k plus 1 to start out. Okay. Then we have these 3 components, and formula for the 3 components, we just put them back in the fraction. And I get a formula for these sequences. Again, this is one solution. Okay, one possible way. What's a converging sequence? A converging sequence is a sequence that has a limit. Okay, we define what a function limit sort of before f of x, limit x goes to infinity or x goes to 3 or something. But here we are talking about in a list of infinitely many numbers. Okay, Uh, so a sequence converges, or it's a converging sequence if it has a limit. And also the sequence over here are all converging sequence. They come to a point. And to be more precise, here's what we meant. Okay, so here's a more detailed, clearer definitions of converging sequence. So by the sequence convert to L, we means for every epsilon. Okay, you will see this phrase in mathematics quite often. It means for every small positive number, epsilon. This is the Greek letter epsilon. It vaguely means small positive number. Okay, and what we use it for? We usually say, meaning some small tolerance level, if you like. Okay, and let's say we take that number and we're going to make a neighborhood with a size precisely epsilon. So epsilon here, and we call this epsilon neighborhood. Okay, and it doesn't matter how small this neighborhood is. The following thing has to be happening. Okay, that is, most of the sequence will be in that neighborhood. Okay, so this is first we will describe colloquially most of AN. What about them? They falls in this prescribed epsilon neighborhood. Okay. And you can fluctuate the size of epsilon, make it smaller, but the sentence most of AN will be in that small neighborhood is still true. So what do you mean by most of AN? By most of AN means all except finitely many, meaning somewhere in the front part, okay, only finitely many can be outside. Those are the big ones outside, okay? But all of them in the tail part, infinite many of that, all of them has to be squeezed into that little epsilon neighborhood that we define. And this has to be true for every epsilon. As I squeeze it smaller, still true, okay? Only finite also. If such is the case, then we say the limit is L of the sequence again. Okay. And this is the same we will say for sufficiently large n. So for terms that for the terms an that's very far away for n very large, then it will be inside this neighborhood. That is, its distance to L will be smaller than epsilon. And this is true for every epsilon. Okay. Of course, when epsilon changed, that large number n will, it had to be larger. So going to limit L is the same as for sufficiently large n, then AN minus L less epsilon. Okay. If the sequence defined by a formula, elementary formula in X, and the formula f of X converges, like in this case, it goes to 1, the sequence is only part of the sequence are only putting integer 1, 2, 3, 4. So the sequence will be only points on this curve. Then obviously it has to converge to 1. The convergence of the functions will drag along the convergence of the sequence. We'll imply that. So, how do we check a function converge? So one way to check sequence convergence now is check the function convergence. And that means we have to take the limits. And a lot of these problems, then it's a good place to review the limits of using L'Hopital's rule. Okay, so here are 3 sequences. We use we find the limit that converges by using L'Hopital's rule. Okay, so for any kind of a strange exponential function, we want to find out if this converges or not, we take the log. Okay, and then we investigate the exponent, the log part of it. see if that converge or diverge. Okay, and that you can check by L'Hopital rules that go to 0. In particular, log of x compared to the function x. Log of x is very, very slow, goes to infinity, but x goes a lot faster. It's true by L'Hopital's rule. Okay. So it goes 0, so the exponent goes to 0, so the x 1 over x converge. Hence, n1 over n converge. Okay, it's on that curve x1 over x. It converges to what? Converge to 1, of course. Now, how about comparing log? We've done this before, okay? And so use L'Hopital's rule. We can easily check this converge. So log compared to square root, again, log is very slow, even compared to square root of it. It's too slow. So this fraction will go to 0. And how about this power functions versus exponential e to the nth power? Okay, and again, L'Hopital's rules, if you to take derivatives of x to the, so if you associate this to the function x to the 20th power and e to the x power, okay, and then you're going to put x to be 1, 2, 3, 4 integer, right? And so on, so on. And the L'Hopital's rule, I use both goes to infinity. I use L'Hopital rules 20 times, 21 times. Okay, each times I take the derivative up and down, the e to the x is e to the x. But each time I take these, I wind up with x. I get one less exponent. So I take derivative again, I get x 18. And then finally, I wind up with some number on top of e to the x. And the limit for that, of course, is 0 because e to the x goes to infinity. Okay. So we differentiate it enough times, you get limit is 0. In particular, the order of the size, not the size, sorry, of the speed going to infinity is listed here. L of x goes slower than x to a power. In other words, if I put L and x like before, and say even to x just to the 1/10, that's a 10th root, okay? And these will goes to infinity. In particular, if I look at as sequence, goes to 0. 0, 0, 0. Could get a lot slower, okay? Then compare power function to the exponential function. Power function are slower. Okay, so x to the 100 power, e to the x or n, if you like, n to the 100 powers, and this goes to 0. These are the L'Hopital rules. Okay, and a lot of time the formula has sine and cosine x in there somewhere. But then the way we treat sine and cosine x, just remember they just bounce back and forth between 1 and -1, so they are bounded. And we use that to estimate other parts of the information, to estimate how you interact with other parts of the formula to find the limits. But we have a thing called sandwich theorems. Okay, it says if b, every term b is of the b is bigger than every terms of the a correspondingly, and the b's shrink to 0, then the a's get trapped between b's and zeros, and so the whole thing gets squeezed in between, has to go to 0. We call it the sandwich theorem. Where do we use this? For example, in particular, we use it to examine things like factorial. If we have this in the formulas for the sequence. How so? Because I cannot use L'Hopital on these, so I have to somehow approach this differently when I compare these expression with something we used to, like 10 to the n. Okay, and the upshot is n factorial is e to the n is slower than n factorial. N factorial goes to infinity the fastest. So n factorial goes to the fastest, e to the n, then then n to a power, then log of n. Okay, so this is bigger than that, bigger than that, bigger than that. And how do I justify this? And how do I show 10 to the n's and times n factorial over n factorial of the limit is 0? And here's how we do it. Okay. Basically, we write out what a to the n is. And suppose n is very large. And so the more than 10, so that on top, like, there's more than 10 tenths, maybe 20 tenths, 30 tenths, I don't know. Then the bottom will be 20, 19, 18, etc., etc. If n is 20, think about n is 20, okay? And they match, each 10 has a denominator, can kind of write it up right underneath it, the same number of numbers, n numbers, right? I'm going to break this into three components, three portions. That portion is the pink portion and the blue portion and the front terms, the green one. Notice from 10 divided by n minus 1, because n minus 1 is bigger than 10, right? So it's bigger. So this one is less than 1, okay? Smaller than 1, just the first fractions. And I notice every one of these fractions individual is less than 1. So the pink product is less than 1. I look at the blue. There are only 10 numbers there, each one smaller than 10. So they are less than 10 to the 10th power. Now multiply these three parts together against using inequality. 10 times 10 to the 11th on top and n's on the bottom. Okay, so this number is going to be less than 10 to the 11th then divided by n. N goes to infinity, and then these fractions over here will go to 0. But m gets bigger. So an has to be smaller than these, but an are positive, so an has to go to 0 also. So that's what we call the sandwich theorem. But the basic point about this exercise is the n factorial blows up a lot faster than even exponential function 10 to the n or e to the n or 10 to the n, etc. Here's property of converging sequences. If they converge, I can add, subtract, multiply, divide them. Okay, when it makes sense. I get the same answers. So if I look at what's the limit of this times limit of this will be the limits of the product. So I can break up the limits into component, finding the limits of component, and then put them back using arithmetic operations. Okay. Diverging, scattering, a sequence that does not focus in on a point, it's called a diverging sequence. Okay, so a diverging sequence is a sequence if it doesn't do something, doesn't correlate into one single point. Okay. One thing about diverging sequences, you gotta be careful. Okay, you can have a function that behave very bad, and but a nice sequence can be defined by a bad function. So like over here, x sine pi x, I can define that if I plug in integers, that I get the sequence 0, 0, 0, 0. Okay, and so in this case, we have the sequence behave very nice, but the functions that we're talking about behave very not very nice. Okay. So in particular, okay, we have the theorem if f of x converges. Okay, then this will imply f of n converges. Okay, this check. But not so the other way around. If f of x diverges, okay. By the way, this is converges, right? If f of x diverges, it does not mean that the sequence you're looking at diverges. Okay. The converse, of course, is true. If a sequence diverges, yeah, then your original f of x must diverge. It must be has no limit, because if it has limit, then the sequence would have limit from previous theorems. Okay. So diverging functions give diverging sequence. Sorry, converging functions give converging sequence. Diverging functions, you're not sure. But we can make it a little clearer. What kind of divergence? Well, we have this divergence that goes to infinity, okay, as this sequence, as n gets bigger. Then we have like this one too, as absolute value gets bigger. I know kind of what the sequence is doing in terms of absolute value. It gets bigger and bigger. So if a function goes to infinity, if limit f of x goes to infinity, okay, in this divergence, okay, of course, we still use the word divergence, then we can say Fn diverges too. Okay, this is true. If the divergence is the type of divergence go to positive infinity or negative infinity, then the sequence definition has to follow those functions blows up. Okay, and a little clear what I mean by divergent go to, what I mean by going to infinity. Going to infinity means it doesn't matter what number you put on the line, the number c, okay, and then most of the sequence must be bigger than these numbers. You can only have finitely many of the sequence that's smaller than this number. It doesn't matter where this c is. I can move the c over. I can move this. I can move the c over here. So I talk about smaller, but still most of them is the right hand side. There's only a few more on the left hand side. Still fine. Okay, if that's true for every number c you place, and there's always infinite many on the right hand side or the tail one, finite on the left hand side, then we say the functions, the sequence goes to infinity. Okay. So I don't want this. Now there's another kind of divergence. Besides this divergence goes to infinity, where everything becomes bigger and bigger. Okay, it doesn't look back. It's a runaway sequence, if you like. And then the other is a chaotic sequences. Like what? Like sine of x. Okay. This one does not converge. There's no limit. Sine of n, if I look at sine 1, sine of 2 in radian, okay, sine of 3, etc. These numbers just simply, there's no rhyme or reason what they are, and they don't accumulate at any particular point. They just bounce back and forth between 1 and -1. This we call chaotic convergence. Okay. And okay. And for chaotic convergence is where we have, in particular, if f of x is chaotic, it goes up and down, then it does not imply f of sequence is chaotic. This, remember, this diverging, right? It does not imply f as a sequence will diverge. Okay, that's where the example is n times sine of n comes in, right? X times sine of x diverges, and diverges chaotically. It goes up and down. But n times sine of n pi, so the pi there, and these just zeros. So oscillating functions formula might give you very nice sequence. Okay, and this is a summary, and that's it. Okay, bye bye, and have a good day. Bye bye.